I think you can see my screen. I will try to increase a little bit. Oh no. I think you can see the screen that I have shared with you. You can see, right? Where is the chat box? Okay. Right. So question number 1. This is very general again. So they have asked, they have given again few elements. This is very common. If you can remember, in 2011, they gave some compounds like sodium thiosulfide, sodium thiosulfate, potassium iodide, and they talked about a little bit about the analysis part. Now this time they are giving another set of elements. Now they are going for some inorganic parts. Okay. So of the 3 isolated ions, Fe3 plus, chromium 3 plus, and cobalt 2 plus, which one has 3 unpaired electrons? So the easiest way is to write down the electronic configuration and quickly sort out which one has 3 unpaired electrons. Okay. So Fe3 plus is in fact ion is in 4s2 3d6, so you can get the electronic configuration of ion first, then you remove the electrons. But remember, when you are removing the electron, it first remove from 4s, then 3d. Okay, so you can quickly get the answer for that. So if you write down the electronic configuration of chromium and cobalt, you can clearly see when you so I will do it in the board, that is easy for me. Okay, okay, so we have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So we are interested in cobalt and chromium. So they ask about iron 3 plus, chromium 3 plus, and cobalt 2 plus. So this is D1, D2, D3, D4. 4s2 3d4, 3d5, 3d6. And this is 4s2 3d7. And you need chromium 3 plus. So 2 electrons can be removed from here and 1 electron can be removed from here. So it is 3d3, which means it has 3 unpaired electrons. Then we will go for iron. Iron 3 plus means 4s0, 3d5. So it has 5 unpaired electrons. And cobalt 4s2 3d7. So cobalt 2 plus means 4s0, 3d7. So 1, 2, 3, 4, 5, 6, 7. So here also there are 3 unpaired electrons. Here also there are 3 unpaired electrons. So as the question asks, which one has? So either you can give the answer as chromium or either cobalt 2 plus or chromium 3 plus, or either you can give both. Okay, the most the correct answer would be chromium and cobalt. Okay, that is one. Of the 3D block elements, titanium, vanadium, and chromium, which one has the maximum 5 electrons that can participate in bonding? So we have discussed numerously about these vanadium compounds, if you can remember. we say vanadium pentoxide, for an example, is used in the production of sulfuric. And when you consider about the oxidation state, vanadium, we say +5 has yellowish color in aqueous solution, then +4 is in like blue color, +3 is in green color, and +2 is in purple color. So you can see vanadium can form different colored species based on their unpaired number of electrons. But titanium, it goes up to +4. If you can remember, titanium oxide. Remember, in your syllabus, you have the extraction of titanium. And remember, one important use of titanium is the formation of titanium oxide particles, where titanium oxide is used for paint industry, especially if you remember about the paints that you know in houses, the brilliant white paint. They uses these titanium oxide particles. And also titanium particles are used in sun creams. Titanium nanoparticles are mostly used in sun creams as well. And chromium, the common oxidation state is +2 and +3 in general. So maximum bonding can be present in vanadium. For an example, vanadium pentoxide. Okay. Of the three elements, carbon, nitrogen, and silicon, which one has the lowest electronegativity? So I am not going to tell this again and again. So across the period, the electronegativity increases. Okay. Down the group, the electronegativity decreases. So carbon, nitrogen, they are in the same and on top period. Silicon is just below, so automatically the silicon electronegativity is lower. Okay. Of the three elements, sodium, magnesium, and aluminium, which one has the highest first ionization energy? So if you remember the trend of the first ionization energy, okay, so you have so this is the general shape that we draw for a first ionization energy curve, right? So you have here sodium, then you have magnesium, then you have aluminium, silicon, phosphorus, sulfur, chlorine, argon. Then in the next period, even lower, potassium. Okay. So always remember there is a pushback from 2 to 3 and 5 to 6. 2 to 3, 5 to 6. Why? Think about the electronic configuration. Here is S2P1 and here P1. There is only one electrode in the p orbital, so it can be easily removed than S2, which is already stabilized. Therefore, here the ionization is a little bit lower. And here, if this is P1, P2, P3, and here again it is P4. Why it is lower than P3? Because P3, it is a partially stable state. So removing an electron here is not good. But here, P4, there is one additional electrode. Again, this can be easily removed to get the partially stable state. So always remember 2 to 3, 5 to 6. Okay. So the elements that you have given is sodium, magnesium, and aluminium. Sodium, magnesium, and aluminium. So the highest energy is, first ionization energy is magnesium. Okay, the next one. Of the three isoelectronic anion, which one has the largest ionic radii? So I told you this in the previous class also. When you consider about the isoelectronic species, which means all species have the same electrons, for a cation, the size decreases, okay, when the charge is increased. For the anions, when the charge is increasing, the size increases. For the cations, the size decreases when the charge is increasing because the effective nuclear charge increases and the electrons are removed when the charge is high. Plus 2, plus 3, plus 4. For an example, sodium plus, magnesium 2 plus. Magnesium 2 plus will be smaller because an entire shell is removed and the charge is high, more positive charge. But when you go for negative species like this, they have given N3 minus, O2 minus, F minus. They all have same number of electrons. But the charge is maximum for N3 minus, where there is a high electron-electron repulsion. So if screening effect is there, so N3 minus will have the largest ionic radii. Okay, so that is the vice versa concept of cations and anions. So again, they have given another in the sixth statement: sodium plus, calcium 2 plus, and aluminium 3 plus. Which one has the smallest? So for cations, higher the charge, smaller the radii. Anions, higher the charge, higher the radii for isoelectronic species. Okay. So the sixth one, the answer is aluminium 3 plus. So these six statements are a little bit easier than the previous 2011 question because it had some analysis parts as well, like to check which compound is used for volumetric analysis, gravimetric analysis, all those things. Okay. This is very general, straightforward general chemistry, included with little bit of inorganic. Okay, so part B. Okay, so part B is peroxonitrous acid. What is this? Some people like, oh, what is this? HOONO. Don't think this is HOONO. This is HNO3. Okay. Is it HNO3? You can use the chat box to tell me whether this is HNO3 or not. Is it HNO3 or not? So where are the answers? So one says yes. What about others? So I see only one answer. What about others? Is this HNO3 or not? Okay, there is another answer saying yes. Okay, what about others? So there are three more people who can answer, right? So I am waiting for your answers. Quickly, the time is running out, please. Just tell me whatever you think, that's all. No idea. Okay, the others? Someone says no idea. What about others? So, what about Fikra and Sumaya? Okay. So, what do you think about this structure that is given? Okay. So, I will not spend much time furthermore. Now, remember this is not HNO3. Okay. If you can remember about HNO3, nitric acid, the HNO3, the nitrate anion, the oxygen is connected like this. Okay. Do you agree on that or not? But here, remember, the structure given is like this, where the nitrogen is only connected to two oxygen and one oxygen is connected to another oxygen. This is the place where it becomes peroxo, because here it does not contain oxide, it contains peroxide, for an example. Okay, so there is no problem for us to do the question here. You don't need to know whether this is nitric acid related or not. Okay, so the question says draw the most acceptable Lewis structure for this ion. Okay, so what is the ion given? That is OONO minus. Okay, so the easiest way, what we do, so if you are an expert, you can just draw the Lewis structure, but I don't recommend you to draw like that. So first we count the valence electrode: 6, 12, 18. 18 plus 5 is 23. 23 plus 1 is 24. So we divide 24 by 2. I'll stop sharing the. Okay. So 24 divided by 2 is 12. So there should be 12 pairs in this structure. But already 1, 2, 3 is taken. So we have to put 9 electron pairs. So I will put 1, 2, 3 to complete its octet. 1, 2, 3 to complete this octet. And 1, 2 to complete this octet. So 3, 6, 8. So there is 1. So I will put here. Okay. So this is our skeleton. Now we will put the charges as well. 1, 2, 3, 4, 5, 6, 7. So here it should be minus 1. 1, 2, 3, 4, 5, 6, 7, minus 1. 1, 2, 3, 4, plus 1. 1, 2, 3, 4, 5, 6, no charge. Okay. Now we will try to complete the octet. Okay. Now here you can see this oxygen, the octet is already completed. Okay. So there is no, no point that this oxygen needs to give these 2 electrons to this oxygen, because it cannot, you don't need to form that because already there are 8 electrons. So the idea is you can give these 2 electrons to this to complete this octet. So nitrogen, there will be 2 double bonds here, there will be 2 lone pairs like this, and there is a lone pair here already, and there is oxygen here, and charge is -1. So octet completed, 2, 4, 6, octet completed. So this is the most stable structure. You can draw this structure. Okay, so this one possible structure that you can draw. The next question is draw resonance structures for this ion, giving reason, comment on their relative stabilities. Now we have to look the resonance structures. Now we have the Lewis structure, so I will erase this one. So resonance structure means you need to put the electrons in different arrangement and see what structures can be taken, and then you need to tell the stability, right? So the first resonance structure is this one. So this is, we can say, stable, because they have told us to comment about this structure. This is the Lewis structure that we draw, and from this Lewis structure we can draw some other resonance structures as well. Okay, so this is stable. Why this is stable? Charge separation is minimum. That is one. Charge separation here is minimum, because there is only negative charge in oxygen. Okay, and you can write down the most electronegative atom. Oxygen has a negative charge, because oxygen, when there is a negative charge, it likes it. Okay, so this structure is therefore stable. Okay, write down all. Write this, and write this. Either you can write this one or this one, but write both. That is how your answer becomes comprehensive. Okay. Now, what is the next resonance structure that you can draw? If you can remember, in our skeleton, this oxygen gave the lone pair of electrons to this nitrogen. But in the same way, this oxygen also can give the lone pair to this nitrogen. So there will be another structure where on one side this will be like this, minus, okay, and nitrogen is octet obtained, but here oxygen has a problem, because 1, 2, 3, 4, 5 now there is a +1 charge here. How this came? Because from the skeleton, first we gave this lone pair to this nitrogen, so this becomes a stable one. In the second case, this stays as same, but this oxygen gives the lone pair to nitrogen, and this is the structure that we have. Okay, now what about this one? This is stable or not? You can clearly see the charge separation between these molecules. It is very high. So this is not stable. That is the first point. The second point is the electronegative atom oxygen also has a positive charge. So this is another case where it does not favor the situation. So this is also not good. So this is a situation where the octet is completed in all, but oxygen, since it has a positive charge, it is not stable, and the charge separation is very large. So this is another problem. Okay. Then we can draw another one. If you really look at this carefully, Here we drew the most stable Lewis structure by giving 2 lone electrons to this nitrogen to make this charge -1 to neutral. Okay, but someone can think I can make this -1 to neutral as well to see whether the structure becomes stable or not. So I will do that one as well. Okay, so this can give electron like this. So there will be a structure like this. There is a double bond here, and there are already oxygen here. There is nitrogen here. Minus, and 1, 2, 3, 4 plus 1. 1, 2, 3, 4, 5, 6, 7 minus 1. And here what you can say, again this is unstable. The reason is why? The reason is here, as similar to this one, you can understand here, if I check this one here, 1, 2, 3, 4, 5, yeah, this should be +1. And here also remember there is a positive charge in oxygen and the charge separation is very high. Okay, this oxygen gives 2, so this becomes minus. So there is a big problem here as well. So what you can do here is, please try to understand what I am going to say. When you think about this structure, you can draw as many as Lewis structures. I mean the resonance structures, you can draw many. But you don't need to draw all. Okay? Try to draw maximum 3 and compare the stability among them. Try to understand what I am saying. Try to draw as maximum 3 and get the stability of them. Always use our general method. If you are really an expert, you can just draw the skeleton. You put the electrons quickly because anyway at the end of the day you need to complete the octet. So you just put the electron without counting anything. I mean the valence electron. Then you just need to try to put the electrons in bonding and try to get an answer for that. Okay. Right. So I hope this gives you the idea for this particular question. I told you in the previous class also, just go through these Lewis structures. Then you can automatically come to a point where you will get 100% marks of this particular question, because if you are omitting this question, that is the freaky thing that you can do, because this question is very easy. The only point is you have to understand to do the structure very quickly and carefully. Okay. So the next thing is we want to deduce the structure or the shape around nitrogen as well as oxygen attached to both nitrogen and oxygen. So we will consider that for our Lewis structure. Okay, so now this is a more stable Lewis structure. Okay, so first they are asking about nitrogen, the shape around nitrogen. So if you can remember, first you write down the number of valence electrons, 1, 2, 3, 4, 5. So you can write valence electrons around nitrogen is 5. Okay, then you can write down number of electrons from oxygen. How many electrons for bonding? 1, 2, 3, because this oxygen gives 1 electron, this oxygen gives 1, this oxygen gives 1. I mean here 2 electrons, here 1. So altogether 3. Okay. So total number of electrons in bonding is 8. Okay. So 1, 2, 3 given by oxygen, and the valence shell has 5. So total number of electrons is 8. Then you can write down number of bonds directly. Okay. So if you can remember, I told you when you write down the number of bonds, you count the sigma bonds 1, 2. Then you write number of lone pairs. It is 1. Okay. So this is the general way of writing. So you have 2 bond pairs and 1 lone pairs, and this is the shape is, you can write according to VSEPR theory, the shape is angular or bent. Okay, you can write like this, angular or bent. But I will tell you a similar way. So this is the writing that you can write, or either you can use this one. So total electron here for bonding is 8. So you divided this by 2 to form 4. So you can use repulsion unit is equal to bond pairs plus lone pairs. Okay. So bond pairs here 1, 2, 3. Repulsion unit is 4. So you can write down lone pairs as 4 minus 3 is equal to 1. Okay. But you don't need to use this method because that is not expected from you. What is expected? You write down the number of valence electrons, you write down the bonding pairs, and you write down the lone pairs. These 3 are the only things that is expected, and finally you write down the shape. That's all. Okay. But remember, actually 8 electrons means there are 4 repulsion units, which includes repulsion unit equal bond pairs plus lone pairs. That is one. The second one is oxygen attached to both nitrogen and oxygen. So this one. Okay. So you can write down number of valence electrons around oxygen 6. Number of electrons from oxygen for bonding 1. Number of electrons from nitrogen 1. So total number of electrons again 8. So the repulsion unit will be 4. You don't care about that. Then you can write down bond pairs 2, lone pairs 2. According to VSEPR theory, what is it? Again, it is angular or bent. Okay, so next one. State the following. Electron pair geometry around the atoms and hybridization of the atoms. So I think now you should be able to do these things if you go through the last year paper very carefully. So you know, for the electron pair geometry around nitrogen, this one, I think this one, right? Yeah, this one. So for the electron pair geometry, if you can remember, I said we count the sigma bonds and the lone pairs. So here we have 1, 2 sigma bond, 1 lone pair. So 2 bonding pairs, 1 lone pairs. It gave you the structure angular or bent. But when you try to express about the electron pair geometry, you have to count the lone pairs as a bond pair. So 1, 2, 3. Now there are 3 bonding pairs. No lone pairs. For electron pair geometry, they are asking about the electron pairs. You need to count the electron pairs. 1, 2, 3. But we don't count the pi bond. Only sigma bond and lone pairs. So 3, which means it is trigonal planar. So what about the hybridization? For hybridization, again, we count sigma bonds and lone pairs. 1, 2, 3. So the hybridization is also sp2. Okay. And the next thing is oxygen attached to both nitrogen and oxygen. So again, this one. So it is very easy. Two bond pairs, two lone pairs. The shape was angular. But when you want to get the electron pair geometry, we count the sigma bonds and lone pairs. So how many we have? 1, 2, 3, 4. So it is tetrahedral. So in tetrahedral, the hybridization would be sp3. Okay. So based on that, right, so based on that, we can quickly discuss the other questions as well. Sketch the shape and the Lewis structure in part 1 above, showing approximate bond angles. Okay, so our Lewis structure was like this. There was oxygen here and 2 for 6 years, oxygen here, and there was like this. Okay, now we found this hybridization is sp2 and this hybridization is sp3, which means, what is it? This, there is a lone pair here, so it can be drawn like this. Here is the lone pair, this is the oxygen, because sp2 means the bond angles is roughly around 120. sp2, remember. And here there are two lone pairs. Either you can draw like this, putting the lone pair like this, and here is the oxygen, negatively charged. And this angle is around 109.5 because this carbon is sp3. Okay, you can draw like this, or either you can shift one of this, because instead of this lone pair, you can think this lone pair is here, then oxygen is here. So it will be like this. The lone pairs are like this, and your O minus is like this. Okay, but this is mostly acceptable because this bonding is away from the oxygen to oxygen. This is minus, this is oxygen. There will be somewhat a repulsion like thing between these two oxygens, but this is more good, but both are acceptable. Don't worry about that. Okay. Okay, so next one. So meantime, if you have any questions, you can ask as well. Okay. Identify the atomic hybrid orbitals involved in the formation of the following bonds in the Lewis structure drawn in part 1. Again, these are very straightforward questions now. So oxygen 1 and oxygen 2. So they are asking about, these are 1, 2, and 3. Okay. So you know this is already sp3 and this has no hybridization. In fact, this is sp3, but to form the bond with these two, this is sp3, this is sp2, okay, and this is 1, 2, 3 again sp2 according to the Lewis structure. Okay, now they are asking the bonding of between oxygen 1 and oxygen 2. So this is oxygen 1, this is oxygen 2. Okay, so here you know this bonding surely sp3, but here what can you say about this? You can use the chat box to explain or simply tell whether what is the bonding orbital of this. This is sp3 or 2p. Okay, there is one answer, 2p. What others say about this? Okay, 2p. Can I ask the question why? Okay, Sanali also tell 2p. So why? Why? What's the reason? Why? Because now, according to this structure, now if I want to get the hybridization of this one, I have one sigma bond, three lone pairs. So it should be like sp3, right? It should be like sp3. Now here, how did I get the hybridization? One sigma bond, two sigma bond, two lone pairs. The hybridization is sp3. Now according to that, I have three lone pairs and one pair. So 1, 2, 3, 4. It should be sp3. Okay, it should be a sp3 actually, right? But now you guys say this sp3 bonding is between 2p of this oxygen. Now I am asking why. Because it can have 4 sp3 hybridized orbitals. One sp3 hybridized orbital will have one lone pair, the other one will have other lone pair, the other one will have other lone pair, and the remaining sp3 hybridized orbital can have the bond here. But you guys stating me this is 2p. The bond between here, this one and this one is 2p. I am asking why. You can use the chat box very quickly. So now I receives an answer like it can be given as sp3 or 2p. Now there is a point here. Okay, remember, actually by just looking at the structure you cannot predict that, right? Both 2p as well as sp3 both are correct, because when you consider about the hybridization you can just tell it is sp3. Okay, but since this is a terminal oxygen atom, terminal, remember the term, this is terminal. Okay, this is a terminal oxygen atom, it can be 2p as well. Okay, but the most acceptable is 2p. So you're correct, 2p is correct. But remember, sp3, a person if giving that answer sp3, you cannot just think that is wrong, because it can be. Because if someone asks what is the hybridization of this terminal oxygen, oxygen number 1, tell me what is the hybridization of it. Okay, in 5, the shape around nitrogen is angular. Then is it the angle is less than 20? Yeah, it's correct. Like for an example, now the idea of this shaping is like if exactly there is two double bonds and I mean two single bonds and a double bond, then it is okay. But actually the shape, the angle should be different than that. The reason is, now if you consider about the repulsion units, always remember bond pair repulsion is smaller than lone pair bond pair repulsion, and even this smaller than lone pair repulsion. Okay, I totally agree with that. Okay, this should be less than 120. That is true, because here if you have, for an, we will take carbon. Now this one you can exactly tell this is almost should be 120. Okay, but here remember this one also less than 120. Okay, and even this one, the 109.5, it is also less than 109.5, because this is exactly 109.5 when you have methane like this, where 4 terminal hydrogen atoms are same. So this is the only condition where the bond becomes 109.5. Okay, but you are correct, this situation and this situation, it should be less than 120 and less than 109.5. That's true, I agree upon that. Okay, so the I hope I answered your question. And the next one is the hybridization between O2 and nitrogen. So where is O2 now? In our structure, oxygen, second oxygen is this one, and nitrogen. So it is clearly sp2 and sp3. Is it? Okay. Where is O2? O2 and nitrogen. Yeah, O2 and nitrogen. So where is O2 here? This one. And nitrogen is here in this one. Yes. Now this comes the last question. I mean, before the last part there is more, but this ask the question where wait, I will share the screen, then it will be easy for you. Yes, so here given isomer of peroxonitrous acid, what do you think about that? What do you think about that? Normally we identify isomers in organic chemistry, right? But here they are asking about an isomer of peroxonitrous acid. So you know the peroxonitrous acid. So peroxonitrous acid is this now. So this is our peroxonitrous acid. Now, if I think about the formula, this is HNO3, right? But the original formula of this is HOONO. This is the peroxo acid. But this formula, now they are asking for an isomer. So in organic chemistry, we always study about this isomer. But we have never come across a question like this before, where now they are asking an isomer in an inorganic chemistry part. Okay, but there is no excuse for anyone, because this is very simple. Because just if you get the number of atoms, you can clearly understand this is HNO3. So the isomer, the clear isomer of this is HNO3, nitric 5 acid. Okay, it should be very easy to get the answer for that part. Okay, so we will quickly move on to the rest of the question, and we will quickly finish this session today. Select two polar species from the list given below. So try to draw the structures of this. As I told you in the previous class also, you need to find the species which does not have a dipole moment. And if there is no dipole moment, that means there is no clear charge separation. That species is more or less non-polar. If there is a clear charge separation, which means it has a clear dipole moment change. So which is, in this case, it can be polar. So if you think about this formaldehyde, okay. So the easiest way to get the answer for this is try to draw the structures, okay. So you know formaldehyde. You can clearly see the oxygen is electronegative, so delta negative, delta positive, delta negative, delta positive. So clearly there is a charge separation, a negative part, positive part. So the dipole moment changes toward this direction. So this is a polar group. And in the same way, carbon cos, okay, okay, COS. There is again a clear charge separation. Okay, either you can draw in this way. Okay. Then come to SF6. So sulfur, you know, it is can be present in the four planes. These bonds are attractive. So all this dipole moment cancel, this dipole moment cancel, this dipole moment cancel. So entire no resultant. Okay. Then you have ICl4 minus. So it will be like this at the end of the day when you put the charge as well. Then SiCl4. It is also very similar. Even though it is a tetrahedral structure, it pulls from four directions, so there is no net dipole moment. Okay, so try to understand this. And the last part of this question is they are asking about the interaction types, intermolecular forces that exist between the molecules given here. So HBr, bromine is electronegative, hydrogen is electropositive. So there is a clear charge separation. So there is a dipole interaction there. H2S, again, there is a clear charge separation. So in between HBr and H2S, clearly there should be a dipole interaction because both are dipoles. That is one. And then since these two are gases, they should have London forces as well. Okay. Then you have Cl2 and CCl4. This is the reverse condition of the first, because Cl2 there is no dipole separation. CCl4 is like CH4 or SiCl4 in the previous case. No dipole separation. So these are non-polar molecules, and in the meantime, they will only have London forces. Okay. And the last one, CH3OH and H2O, clearly you can see this one is an alcohol, one is water. So clearly they have OH. So there should be hydrogen bonding. That is one. The other thing is there can be even London forces as well. Okay. So try to get the idea. London, you just don't have to tell London. You can use Van der Waals forces as well as you wish. Okay.